Quantum operators are just like numerical operators that you learned in the first grade. You see, having numbers is cool, but operators let us manipulate those numbers. Similarly, wave functions are nice, but we need quantum operators to be able to work with them. In this video, we'll understand what operators are. We'll take a look at the specific properties that quantum operators must have and much more. The properties of operators are somewhat technical, but stick around till the end and I'll break it all down for you. The first thing I want you to note is that quantum operators are what's called unary. This means that they act on only one thing, and that thing is the wave function. As an example, the operation of taking the absolute value only needs one number. You have a number and then you take the absolute value. So it's a unary operation. Quantum operators are like the absolute value in the sense that they are unary. They only act on one wave function. Before we move ahead, let me mention that knowing linear algebra is very important for this video. I will cover the concepts of linear algebra as well, but only very briefly. The next property is that the operators must be linear. In fact, this is what the postulate states. It says that to every observable in classical mechanics, there corresponds a linear Hermitian operator in quantum mechanics. By the word observable, we are talking about properties like position, momentum, energy, and so on. So for every such observable, we have a so-called Hermitian linear operator. Remember that a linear operator is an operator that satisfies the following property. In words, linearity basically means that you should be able to switch the order of the constant and the operator and be able to pull out the operator from the sums. If you need to read more about linearity, I'll leave a link in the description for you to learn more. Now let's understand what Hermitian means. A different and perhaps a better name for Hermitian is self-adjoint. As the name suggests, a self-adjoint operator is an operator that's its own adjoint. Now, what's an adjoint? Well, the adjoint of an operator is defined using this somewhat abstract property, where these angled brackets represent the inner product. And for the sake of completeness, let me also remind you that the inner product is defined as follows. Feel free to pause the video here if you need some time to read and digest all these definitions. Again, I'll leave some links in the description where you can read more about all of these mathematical definitions. Lastly, here are a few examples of some of the most important operators. Where in the last operator, V of r is the potential in which the particle is placed. The key point in this postulate is that these operators must have this property of being self-adjoint or Hermitian. But why? You see, the Hermitian operators have the property that the eigenvalues of these operators are real numbers. We'll see in the next video that it's the eigenvalues of the operator that determine what values we can possibly measure for a certain observable. Since the physically measurable values have to be real numbers, and since they are given by the eigenvalues of operators, we have to postulate that the operators should be Hermitian. If you liked this video, make sure to like and subscribe, and I'll see you in the next one.